Our next presentation, Parallelism in a Region Inference Context by Martin Elsman and Troels Henriksen. Martin will give the talk.
Yes, so this is joint work with Troels Henriksen. Recently there has been a lot of work on adding parallelism, task parallelism support in ML compilers, including OCaml and Milton in the form of Maple MPL. And the main difficulty there is to combine higher order functional programming with mutable data structures, and then also the task parallelism, while still allowing for efficient computation and good use of memory resources, and in a safe way, in a shared memory environment. So in this work, we'll try to look at using region inference and seeing this problem from a region inference perspective. So overall, the problem that we are going to look at here, we have a function par which will execute two threads, two functions in parallel. And really the question is, what are the memory effects of evaluating the expressions E1 and E2 in parallel? So this is the problem that we are going to look at. So first a little bit about region-based memory management and region inference. So traditionally, region-based memory management will allow the programmer to associate the lifetimes of objects with so-called regions. And then it allows also the programmer to reason about when to allocate and deallocate memory. And this is a little bit in contrast to region inference, where the programmer programs in a source language which is not annotated with any regions, and then region inference will then add annotations to the program at compile time and produce these region annotated terms. So that has proved out to work quite well for sequential program execution, sometimes for programs that behave quite dynamically. It's a good idea to add also a traditional reference tracing garbage collector, for instance. The point there is then that garbage collector can then be allowed to run less often than otherwise. So this memory strategy has not been previously investigated in the context of parallelism. So the contributions that we are giving here in this paper is that we are introducing this fork join parallel construct, which is suitable for region inference, and where we can basically identify the scope of the thread execution. And then we also having a soundness proof for a non-deterministic region explicit language, and that will serve as a target for region inference. We also present in a protection inference algorithm, a refinement of region inference, that will separate regions, those regions that are guaranteed to be allocated into only by at most one thread, and those that are where no such property exists. And then in practice, we have integrated the techniques in the MLKit, a standard ML compiler, which is based on region inference. And then we have evaluated the strategy on a set of parallel benchmarks. So from the programmer's perspective, the programmer will program against this thread interface, where there's a spawn function that will spawn a thread, and then there will be this continuation function which will execute in parallel with this executing thread. And it's possible for the programmer then to use this get function to join, to have the thread join the parent thread. And the model is then that also when the scope of the thread execution here terminates, then it will also join the thread that has been spawned. So in that sense, there's a guarantee that after the thread has executed, one can reuse or one can free memory that is used locally by the thread. So on top of this, it's possible to build other parallel building blocks, the par function as we saw before, par4 functions and parallel maps and so on. So region inference in this context uses a memory model where the heap is allocated or represented as a stack of regions. Each will consist of a linked list of equally sized pages, and then the heap basically grows here. You have a stack of regions, and at runtime then all values will be allocated in those regions. So each individual region may grow, and the stack may also grow, but you can only basically pop the topmost region and free those pages in that region, and then make that reusable for that memory reusable for other purposes. And then the idea is to then perform region inference, insert these allocation and deallocation directives at the program. And that's based on an effect type system. So the source language will be basically based on the Tofte-Talpin region paper from PLDI'23, and then extended with this let spawn construct that will spawn a thread and which can then be accessed from within E2. And then every well-typed source language expression will be translated into this to an annotated expression. We have the derivation here, the typing rules for the inference. So the possible annotations in the target language will be that there's a let region construct surrounding an expression, introducing a region, which is now put on the stack. And then inside E, we might have all allocating expressions may then refer to this region, and then that will denote where the values that are computed will go at runtime. So here's a small example where we have a variable y here, which is the result of computing this intermediate language expression here, the target of region inference. So here we see that there's a local pair created, and for this case we see that the integers are also allocated. Of course, in a real implementation you won't allocate integers on the region, they will go in registers. But here we see, for the sake of the example here, that the integers go inside regions. We have here that the pair is created in this region row 2, which is local to the execution here. We also see that the 3 here is also local in row 1. And then we see that region inference has figured out that eventually this value 4 will be global to the local expression here, meaning that once you extract the second component of the pair, that thing needs to be alive for the remainder of the computation in the dots here. So there are various mechanisms in the region inference to make it work in practice. So for instance, functions can take regions as arguments, and that works out by we have an example here where we have a function here, f, which will store its result in a region row. And the point here being that whenever f is called in some context, we can use a local region which is not alive as long as the function exists, but it is introduced locally. Without being able to take regions as argument, we will be forced to surround the entire expression with a region row. And whenever we call f, we will pile up values in this region which is global to the function. So we see that types here in the system is annotated with effects. So we see here that this is a function f, which takes the unit as an argument, and then it will store its value inside the region row and return an integer. And it has an effect that it will store value in the region. And then in constructs of this let spawn construct here, we can then refer to the thread bound to x. And when a thread is joined with a parent at the end of the let spawn construct, the thread's local regions will then be deallocated. So that can be guaranteed. We can also, when we have a non-local mutable object which is being created and maybe assigned to, that might be a mutable value, so we assign a value, a locally created value inside a global mutable object, then region inference will figure out that this value will need to be stored in a global region, meaning that the value doesn't need to be promoted at runtime, copied from some local thing or otherwise being transfer of ownership. That will basically happen by the region inference system. It allows for some destination passing strategy where a parent can allocate a region, and then the function that will the function will then allocate its value and store its store the value in that region. So to make this work in practice, there needs to be some kind of semi-log-free allocation to work on to allow for multiple threads to allocate into the same region. So a region is basically here a descriptor on the runtime stack. We have a pointer to the first page, so the list of pages in the region, and each region then has an allocation pointer pointing to the next free element in the region. And whenever some allocation occurs, this allocation pointer needs to be updated, and a value can be returned for storing storing objects. So now, of course, if there are multiple threads allocated into this region, there will be races on this allocation pointer, which needs to be guarded somehow. So we allow for such, if it's identified that multiple threads can allocate into the region, then we have allow for mutex to be stored here in the region descriptor. But of course, we will also use cat instructions to try to make things fast. And for non-protected regions, those we can identify are not going to be allocated into by multiple threads. We can leave out this mutex. So here is a protection inference. I won't go into details here, just tell you that there's this protection inference, which is a region inference refinement. There's more about this in the paper. Basically, every LED region construct is refined to now also have a P indication here, saying whether that protection is needed or whether no protection is needed. And then whenever a region is allocated, this mutex object is either inserted into the region descriptor or there's just a null added. And then we see here that in the inference rules that the let spawn construct will basically put in a constraint. It's a constraint-based analysis saying that the set of effects appearing in the threads executing will need to be disjoint. So this is what gives us this inference of whether a LED region construct should be protected or not. So here's a small example where we see the use of this is merge sort with region polymorphic recursion, where we can really see that the protection inference has identified that the parallel calls to the merge sort function will allocate its result in different regions, and thereby there will be no need for protections for these allocated regions. So here's some evaluation. So we can see that for a number of benchmarks we see okay speed up. There are also some benchmarks that are not really that parallel and have problems scaling. But we see that it's for those benchmarks we have implemented here, we see similar performance as with MPL. And with that, there's much more in the paper, and a lot of future work, of course, and related work. And please, questions, thanks.
Questions?
Hi, Sam Westrick, Carnegie Mellon University. Great talk, Martin. Previous work, I think, has shown that you can integrate, and you mentioned this, region inference with garbage collection. So what do you think about integrating parallel garbage collection now with parallel region inference? What do you think? Difficult or doable, or?
I think there's probably a lot of engineering that needs to be done, but and the question is what the strategy should be. There will be some regions which can definitely be garbage collected in parallel. Those that are basically the leaves, but it turns out that those are not. The region inference will probably do very well with garbage collecting those things. So the real interesting things are garbage collecting the global regions, and for that, that's a little bit more tricky. Of course, we can stop the world, and maybe that's the first strategy to try out. But of course, also a lot of engineering to get that working in a full-blown compiler. Yeah.
Excellent. Thank you.
Matthew Parkinson, Microsoft. With your region protected, non-protected, you've kind of got that scoped at the same level as the region itself. I wondered if you considered adding a scoping to turn something from not protected to protected sort of temporarily.
That's a good question. We haven't actually considered that. Yeah, that might be something we should consider. It's a little bit similar to the Egan-Gay idea, I think, earlier, where we separate the lifetimes. Also, here we have a stack-based approach to regions, where we could have also a refinement of that, where we allow for resetting regions, also, or maybe deallocate regions, not in a stack-based manner. And a similar thing with this thing. I think those could be that could be investigated.
Cool. Thank you.
Hello, Martin. John Hughes, Chalmers. I wonder if you thought about region inference for message passing at all. It sounds as though you would need to have one region global to both communicating processes in which all the messages would accumulate. But have you thought about how to avoid that?
No. But I have seen some of the examples that kind of tend to communicate via global data structures tend to have this problem that the data will end up in these global regions, and there we have the garbage collector, but that's of course not the most elegant way of doing it. Whether you can do something with existential regions and have a more dynamic deallocation of regions, that's to be investigated, I think, and probably some of the ownership work in other languages might be better suited for that. Yeah.